Okay, I think that's enough of a break. So we'll continue now. Right, next lesson now. Yeah. Oh, I haven't even started yet.
Oh, I like derivatives compared to a trait.
Yeah.
74.
I wish we could just go back to graphics.
Yeah, I love how we started with slope and now we're doing it.
Okay. So we're going to have a look now at the second derivative, and there's nothing too special about finding the second derivative. So the second derivative, which is written like this, d2y dx squared, that's just equal to the too much movement off the way. Guys, come on. Sit down. Shh. Okay, we ready now? So, as I was saying, the second derivative, there's nothing too special about it. It's just the derivative twice of your function. So, very simple example. Let's take y equals x4. Well, the first derivative is 4x cubed, and the second derivative would be 12x squared. Okay, can you write this down? No, please. I know. Look, you don't know how long it takes to get your hair just right in the morning, okay? Ready? Okay, so there's nothing too special about the second derivative in finding it. But what's interesting about the second derivative is what you can use it for. So we'll have a look now at what exactly is the meaning of the second derivative. Okay, so I'll just scroll down a bit here. So if you want, this is kind of like the definition. You know, it's just the derivative twice. Not really special, yeah? No, actually, that's just a little dash to mean first derivative, and this is like 2 dashes for second derivative. Yeah. Okay. So, scrolling down, we need to think about what the graph could represent. So, let's say we have some simple graph like a cubic. So we'll say we'll have a cubic graph here. This is x and this is y. Now let's consider what the derivative looks like. So let's say we have x is 0. The derivative would be positive or negative here? Well, it's the slope of the tangent. So what's the slope of the tangent here? Positive. And here? Positive. And here? Positive. And here? 0. So describe in words what's happening to the derivative function. It's going from positive to 0, so we say it's decreasing. And then here it goes negative, and here it goes negative, and then here it's 0 again. So if I was to match this down here, here the first derivative is 0, and here the first derivative is 0, and to the left it's positive, in between it's negative, And here, positive. Now that's hardly shocking, because if you have a cubic function and you differentiate it, what type of function will you get? You get a quadratic function. So this is not a surprise to us. But now what would be interesting is if we go down another level and have a look at the second derivative. I'll scroll down. Yeah. Well, actually, I'll zoom out rather. Okay. So the second derivative is the derivative on this graph, which means it's the slope of the tangent on this middle graph. So what's the tangent here? Negative, negative, and here? Yeah, 0. So this point represents a 0 here. And here? And here? Positive. So it goes negative, 0, positive. So it's increasing. Yeah, and again, that's not surprising, because what's the derivative of 3x squared of a quadratic? It's a linear. But we need to figure out what is the relationship between this graph and the original graph. Now, if I try and map the point back up, I reach it at here. Now, look at this graph. This region is negative and this region is positive. How is this region on the left here different to this region on the right? Not quite that.
It turns from negative to, it turns from positive to negative, and here it turns from positive to, from negative to positive.
Well, here it's negative, positive.
No, it turns from negative to, it turns from positive to negative and negative.
Here?
No, before.
Here?
You're saying it starts negative over there, it starts positive.
And then it turns.
Yeah, we can think of a better way to describe this. It's a little awkward. So, look, you're thinking about this too much. Let me draw the graph underneath this one. So, it's something like this, we'll just say. And this point, we'll say, is here. And this region, where the second derivative is negative, corresponds to this. And this region, where the second derivative is positive, corresponds to this. So what's the difference here in the two shapes? Oh, no, come on. Look at this shape. And then look at this shape. That's it, yeah. In this graph, you have it as a hill shape. And in this graph, it's like a valley shape. So we call this shape here, this hill shape is called concave. And this shape is called convex. So in other words, the second derivative tells us if we are concave or convex. So the first derivative tells us the slope of the tangent, and the second derivative tells us how concave or convex we are. So if we were to summarize that as a point now, your y dy dx and d2y dx squared. So what would you say y tells us about the graph? What does the y represent?
The function itself?
Yeah, so like geometrically, what would you call that? Now guys, you're thinking way too much, or not enough, I don't know which. Yeah, but what geometric word describes that? No,
why?
The source, the graph itself, the essence of being. What's the y representing here? The height of the graph, of course, the height.
Oh.
Right, the height. Yeah, and what does the first derivative represent?
Slope.
The slope, the gradient. And what does the second derivative represent? It represents what we call the concavity, whether it's concave or convex. So in other words, the sort of shape of it. Now, think about the meaning here. If this number is quite big, what do we have? We have a situation where it's quite
A big
high on the graph, yeah. Okay? So, you know, it'd be something like way up here. If this is quite big, what is that telling us about the graph?
It's very
Steep, yeah, so it's climbing rapidly. Okay? Now, if this is positive, very positive, that's this part here, it's telling us the graph is very convex. So if this is rather positive, it's telling us it's convex. So for example, this graph here is a little convex, whereas this one here is very convex. And if this is 0, then it's not convex. You know, so it might just be flat like this, or it could be like this. You know, there's no shape to it, no convexity, concavity to it.
Sir,
Okay, yeah.
if you go back to the line you drew for the function above, above for this one.
Yeah.
Like, isn't it both concave and convex on this one, or?
In which one? This one?
Yeah, this line, because the one under is concave.
No, but what I'm saying is the second derivative tells us in the original are we concave or convex. So when the second derivative is negative, that's concave, and when it's positive, that's convex. Now look, you've already talked about this, but you haven't realized it. So for example, if I have this quadratic, you all happy that this is the shape?
Yeah.
Yeah, it's just this shape is called convex. And how did you know it was convex? Well, because this guy here was positive, right? What's the derivative here? 4x plus 3. What's the derivative here? 4. That's positive. Now this was only positive because that guy was positive. If I change this to minus, you would have concave. What's the derivative? Minus 4x plus 3 and minus 4. So you haven't realized it, but you actually do know how to tell if it's concave or convex by looking at the first one. The only problem is that trick only works if it's quadratic. It doesn't work for the other functions. Yeah?
What if it was not quadratic?
Yeah, so we'll have a look. Yeah.
It was 0, then it's nothing?
Yeah, it's not concave or convex. There's no bend in it. It's just like that.
What if it's still quadratic by the time? Or what if
It can change. It can change. So like here in my example here, it switched being concave or convex. Now we'll have a look at some examples, okay? But the advantage of this is that it can tell you if you have a maximum or a minimum. So if it's concave, the turning point is, and if it's convex, minimum. So this gives us our rather important result here. So to find the max and then to find the min. So for the max, you need the first derivative to be 0, but then you need the graph to be concave. And what do we say the second derivative needs to be for it to be concave? Positive or negative? Negative. So the second derivative has to be negative. And then to find the min, again the first derivative has to be 0, but the second derivative has to be positive. Let us have a look at an example in a moment. You definitely need to write this table down. This corresponds to being concave, and this corresponds to being convex. Yes?
I don't understand the part about the first derivative having to equate to 0.
That's what we did last time.
Yeah.
Were you in last class? Did you watch the video? Okay, so write that down. Okay. Do you have that? I'm going to give you guys a cubic equation. And what I want you to do is first find the turning points. But don't bother checking if it's max or min, just find the turning point. So to find the turning points, you just need to make the derivative equal to 0. So I just want you guys to get me the turning points for, let's say, this one here. And then we'll talk about the max and min in a moment. So y equals 2x cubed plus 9x squared minus 60x plus 6. Give me the two, well, there could be one turning point, there could be two. See what turning points you get here. Okay, you've got the two turning points? Did you get the y values as well? Right.
Is it 2 and minus 5? X?
Let's have a look. So, the derivative here is 6x squared plus 18x minus 60 equals 0. So if I divide by 6, I get x squared plus 3x minus 10 equals 0. 5 and 2, right? X plus 5, x minus 2. So x equals minus 5 or x equals 2. Now, let me just have this ready here. Okay, so we have to sub those back in to get the y's. So what do we get here? 62, is it? No?
62 is for 2.
All right.
Minus.
Minus 62? Okay.
No, minus 62 for the X. Yeah, 2.
This guy is
Yeah.
minus 62?
Yeah.
And this one is 62? 281. Okay. Now, you could probably have a guess at which guy is the maximum here from looking at the two answers. So the first answer is minus 5 and 281, and 2 and minus 62. And you can say, oh well, I think it's obvious here. Now it's obvious for this one because it's cubic. But I mean, it's not always what you think. It's not necessarily just a bigger y value. Sometimes it's not. And we can see why that is in a moment. We need to check with the second derivative, okay? So if I get the second derivative here, that would be 12x plus 18. Now, if I put this value in here, I'll get minus 60 plus 18. Is that positive or negative? Negative. So that shape is concave. So it means this one, unsurprisingly, is a max. Now, if I sub this into the second derivative, I'll get 12 times 2 plus 18. That's obviously going to be positive, which means this one is convex, which makes it minimum. So if I was to draw this graph, I know... sorry, this is minimum, which makes it convex, yeah. Minus 5 and 281 is a max. 2 and minus 62 is a min. And the cubic graph goes up, down, up. And we know actually where it crosses the y-axis. Where does it cross the y-axis? At 6. So you can see that your graph max here, min here, ugly, roughly. Now, it's important that you understand max doesn't mean absolutely maximum. Although this is a max, you actually have points here which are higher up. So we call this one here a local max, because it's only the tallest in the area. And this one here is a local minimum. Again, because it's only a minimum nearby. Does this graph have a global max? Is there a point on the graph that is above all other points? No. Because no matter where you are, you can always go up a little higher. And is there a global minimum? No. But if you think about a quadratic, if you found the minimum here on the quadratic, not only is it a local minimum, it's also a global minimum. It's absolutely minimum. So, sometimes in the exam they might ask you to make a graph and to label the minimum and maximum on the graph. It's a good idea to label if it's local or global as well. So in this quadratic one, you would say it is a global minimum, because there's no other point on the graph lower than it. Yeah?
Sir, should we complete the square for the quadratic, find this, the actual vertex?
No, you can use the derivative again.
Oh.
Yeah. Yeah, it means it's minimum globally, like in the whole graph. Okay.
The concave is for the maximum.
Concave is for the maximum. Yeah? Okay, just write that one down. It is it. Yeah, there's a little picture here. Someone showed it to me. Perhaps you remember. I'll put it up. So you can remember that this one is concave because it looks like a cave. Yes. Oh no! Hold back the laughter. It's okay. And so the other one is convex. No. Yeah. Caveman. Looks like a cave. Okay. No, it's lost on you. It's okay.
Max cave.
Right. Okay. Let's do another one here.
Can we do an exponential function?
An exponential second derivative?
Yeah.
Okay. Well, if you just had something like y equals 2e3x, what's the first derivative here? 6e3x. Now, does this graph have any turning points? No, because this cannot be equal to 0. Let's get the second derivative, 18e3x. Now, is this positive, negative, or could it be both?
Both.
I know. Look carefully.
Oh yeah, positive.
It's only positive, which means it's only and always convex. Now, that is not shocking, because when you think about the exponential curve, it is like this. It has a convex shape to it. I didn't draw it like that. I drew it like this. So it's convex.
But it doesn't start negative, does it?
It starts like really near 0. Yeah. Now there's some interesting points on the graph that you might need to find. But just before that, we'll do one more example here. Can I scroll down? I just want you to take the cubic I gave you a moment ago. So where is, okay, what's the cubic I gave you? Y equals,
2x cubed
yeah, yeah,
plus 9x squared
yeah,
minus 60x
yeah.
plus x.
Now, I want to know where is this cubic concave. So you understand that if you draw the cubic, part of the graph will be concave. The part here. And then it switches to being convex. So I want to know where will it be concave. So if I want to figure that out, what could I take as a starting point here to get me going? If I want it to be concave, I'm looking for where this is what? Negative. So if I can figure out where the second derivative is negative, I've figured out where it is concave. Right, well, what is the second derivative? Well, the first derivative is 6x squared plus 18x minus 60, and the second derivative is 12x plus 18. And I want to know where is this negative. Well, that will be when x is less than 18 over 12. What's that? 9 over 6, 3 over 2?
Yeah. So you do start by getting the first derivative.
No, you start by writing this first. Yeah. Now, if we go back to my graph that I drew, but I'll draw it nicely now. Y equals 2x cubed. Y equals 2x cubed. What's next? Plus 9x squared minus 60x plus 6. Okay. Now, have a look at this graph. Focus, focus. If you look at this graph, let's see. What answer did we get? Minus 3 over 2. Here is concave and here is convex. Where's minus 3 over 2? That's roughly here. So would you agree that this part of the graph up to minus 3 over 2 is concave? So what happens afterwards? It becomes convex. So actually this represents a rather interesting point on the graph. It's the point where it switches from being concave to being convex. This point here. It's not quite turning point because here's the turning point and here's the turning point. So the turning point is where it levels off. So does anybody know the name of this point? Where we switch from being in a concave shape to being in a convex shape. Not stationary, because these ones are called stationary. Does anyone know it? No? These are called inflection points, where we inflect from being concave to convex. So for an inflection point, that is where we switch from being concave to convex. What do you think we need to be happening with the second derivative here?
0.
Very good, yeah. We need the second derivative to be 0. But we do need something else with the first derivative. We need the first derivative to be not 0, because it's not really an inflection point if we don't want the slope to be 0. We want the slope to at least be going down or going up, because we want to switch from being like a hill to a valley. So this is what you need for an inflection point. The second derivative to be 0 and the first derivative to not be 0. Now, I know this is getting quite complicated, so what we're going to do next is we're going to make a table where we look at all the possibilities. You know, if the first derivative is 0, if the second derivative is 0, if one of them is not 0. We'll have a look at all the 9 possibilities.
Couldn't we have something like this?
Yeah. No, that's not an inflection point because that part of the graph is not switching between being concave and convex. If you have something like this, yeah, this is true, this is concave and this is convex, but there's no switch here because it's flat. You would need to nearly stick that onto that. You know, so that's why we insist on not having zero first derivative.
But just a question for the one before where you asked where is y concave?
Yeah.
You got a range. You
Yeah.
didn't really get a point.
Yeah, because I didn't say when does it switch. I said where is it concave. So it's concave everywhere on the left. The graph is a concave shape. Okay, continue. Now look, to help you out here, let's have a look at the possibilities. So, do you need me to go back? Yeah. Do we have this inflection point?
Sir, another question.
Yeah.
So the range would be from
Minus infinity to minus 3 over 2. It's a concave shape. And then from minus 3 over 2 to infinity, it's convex shape. And then at minus 3 over 2 is an inflection point. It is switched from being one to the other.
yeah, so minus 3 over 2 and 0.
Well, whatever the y is, it's not necessarily 0. Yeah. Okay, continue down. So, right, we have to look at a few different situations here. So on the top, I'll put in, you could have the first derivative. Let's scoot over here a bit. And here I'll put the second derivative. Okay, so the first derivative is negative. The first derivative is 0. The first derivative is positive. Here the second derivative is negative. The second derivative is 0. And the second derivative is positive. Okay, let's think about the graphs. What's very useful about the first and second derivative is that it tells you a lot about the shape. So, if the first derivative is negative, that means the slope of the tangent is negative. So what would be happening to the graph? No, just the first derivative now.
Concave?
No, just the first derivative. You didn't know about concave when we did first derivative. The first derivative is negative, so what is the graph doing?
Slope is negative.
So again, it's going down. Because the slope is negative, it means it's downward. Fine. Keep that in mind. The second derivative is negative, so what does that tell us? It's concave. So it's downward concave. How could I draw that? I could draw it like this. This is downwards, isn't it? And it's concave. So the graph would look like this here. Right. The first derivative is 0. What does that tell us? No.
Horizontal.
No. Well, yeah. What's the graph doing? What point are we at?
The
vertex, the turning point. It's flat. And the second derivative is positive. Negative.
Still concave.
So it's still concave, but it's flat. In other words, we're at the top of a graph here. You know, it's level and it's concave. Right, the first derivative is positive and it's concave. So it's first derivative positive is upwards and it's concave. So it's concave upwards. So concave but going up. So it's like this. So you see, we're getting a lot of information from the first and second derivative. Okay, let's do the one down the bottom. So everybody on this row, the second derivative is positive, so what shape is that? Convex. So this is convex downwards. So convex downwards. This one is convex upwards. And this one here?
So it's just,
Yeah, it's the turning point again, but it's a minimum. So this one represents a minimum and this one represents a maximum. Okay, the first derivative is negative. So that's downwards. the second derivative is 0. So what's the meaning when the second derivative is 0? Not quite. Second derivative is 0? No. Inflection point, yeah, inflection point. So it's switching from being convex to concave. But the first derivative is negative. So it's downwards. So if it's switching, so it'll have to be like this here. This is the inflection point and the graph is going down. So a lot of people would describe this as a descending inflection point. You're at an inflection point going down from a hill to a valley. This one here, you're going up. So if you're going up, it could look like this. So this is an upward increasing inflection point. Right. And lastly, the first derivative is 0 and the second derivative is 0. What do we have?
Line, right? Because if the slope is 0,
No.
zero.
No. Seems like it, doesn't it?
It's nothing?
No. No. No information.
It's nothing.
No, not that it's undefined or not that it's nothing. It's just the first and second derivative have not told you anything about the shape. So the shape could be anything. So if this happens, the only way to figure out what the shape is by taking some points on the graph. You would have to take some points for x, take some values for y, and make the graph. You can't tell from the first and second derivative when they're both 0. Now, I can show you an example of that in a moment, where you have two totally different shapes and the first and second derivative are both 0. Do you have this graph drawn?
What time is this at?
This table will be at 37. Okay, can I scroll down? So look, here's an example. Take the graph y equals x cubed, and we want to know what is this graph doing when x is 0. Okay, what's the first derivative here?
3x squared.
And when x is 0, what will this be? 0. Okay. And when the second derivative is 6x, and when x is 0, we get 0 here. So we actually don't know what the graph is doing. And you might think, well, this means it's flat, and this means it's an inflection point. Well, if I draw the graph, it looks like this. Yeah, that's true. It's flat, and it's an inflection point. So you say, what's the problem, Stephen? Well, have a look at this one. Y equals x4. The first derivative is 4x cubed. When I put x as 0, what do I get? Also get 0. Second derivative here, 12x squared. When I put x as 0, so you might say, oh, it's the same picture. It's a flat inflection point.
So it's only for tangent?
No, but this graph here looks like this. You were totally wrong. This is not an inflection point, is it? It's a global minimum. So this one here, you've got a global minimum, and here you've got what you might call like an increasing inflection point. You have two totally different graphs, but they have the same first and second derivative. And this is my point. When you get zeros for first and second derivatives, you know nothing about the shape. Nothing about the shape. Can the what? Sadly, no. There is something we can do to get the shape, which I'll talk about now in a moment. So this is an example of why, in the last table, I said when they're both 0, you don't know anything about the graph. This sometimes happens in the exam, but it's quite rare. When it does happen, the only thing you can do is sub in a couple of points to try and figure out the shape. You know, in the exam they'll ask you what is the shape of this graph. And you do the first derivative, you do the second derivative, and you figure, oh, they're both 0. I'll need to draw it carefully to figure out the shape.
So, is it okay to just say inflection point
In which now?
that is
This?
yeah, it's just right like that.
I don't think you'd say you could say there, in this graph you could say there's an inflection point at 0. Yeah, you could say that.
The vertex should be 0 for the first one, the x to the power 4, right?
Say again?
The vertex should be 0.
Yeah.
The global minimum
Yep.
is 0.
Yep, in the first one. Yep. Okay, we can continue? Continue? No, okay. Inflection, sorry. Got that? Now, there is, in the situation when the first and the second derivatives are about 0, you can just draw the graph, okay? But there is a way to check if you take a third derivative. So I'll just show you this briefly. So in this situation, when the first derivative is 0 and the second derivative is 0, but the third derivative is not 0, you can get some information still. So in this case here, if the third derivative is positive, that is an increase in inflection. And then you can guess what if it's negative, what it would be here. Decrease in inflection. Now look, let's go back to the example I did here. What's the third derivative here?
6.
So 6 is positive, that means it's a increase in inflection. Alright, here what's the third derivative? 24x, and when x is 0? 0. So I can't use the third derivative. Yeah?
You want 4?
Yeah, but I'm not. It continues forever.
Yeah,
So this is what I'm saying. In the exam, they do not expect students to have this much knowledge. They would simply expect students to stop here, to make a table, and to draw the graph carefully.
But if we do this,
But if you do remember this, that's fine.
will they give us a mark?
Yeah, you will. But that has yet to happen. Because firstly, it's quite rare for this to happen. Secondly, it's quite rare that students remember about the third derivative. And thirdly, it's quite rare that students will do a hard question correctly using a method they've not used much. So, I don't expect to see it. I just expect to see a graph with a table. So, you see, we're getting tougher now with the calculus and the second derivatives. And then the next one is harder again. So I'll let you try these for a few minutes. What would be good for you to do?
Why is there practical problems for every lesson now?
1 A, F, J, and V. 2 A, C, L. 3 A, B, C. Yeah.
You see number 1.
That is there.
You wrote it
I sure did.
A,
A, F, J, V. Mo, if you're wondering about the fourth derivative, so if the first, the second, and the third are all 0, and you have to go to the fourth, then the fourth one is the same as the second one. So positive is convex and negative is concave. So if you were to go back to this example here, if you were to get a fourth derivative, that would be 24, which is positive, and positive is convex, which is what this shape is. Now, you might say, what if the first, second, third, and fourth are 0, and you have to go to the fifth? Then it goes back to the situation of the third.
So odd numbers inflection, even numbers.
Yeah, so the odd ones you use this increase and decrease in inflection, and the even ones you use the same as the second one.
Yeah.
You think you know this and you'll remember it, but you're already starting to forget it.
No.
We'll see. Okay, try these for a few minutes.